Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense systems DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
Hey, welcome all. This is Ted Welsh, the Information Analysis Center Ops Manager. I'm happy to welcome Dr. Jason Augustin, who will be providing a artificial intelligence and machine learning webinar to you all today. Again, I'll provide a brief bio on Dr. Augustin and also want to flag just administratively that there is a chat feature that we would request. Certainly, any questions, log them in. We will have sufficient time at the end to address them and hopefully have an interactive discussion. So as we go along, as questions come up, please use the chat feature and record your questions. Again, with respect to Dr. Augustin, he is the Chief Technology Officer of Blue Path Labs, which is a research analysis and strategy company that combines mission and business insights with advanced technologies to deliver measurable performance improvements for federal, state, and government agencies. He leads Blue Path's data science and analytics strategy, which uses both traditional statistic modeling and cutting-edge machine learning, artificial intelligence techniques to discover critical insights from structured and unstructured data. Prior to joining Blue Path, Dr. Augustin was the founder of Future Scout, which was a data science and analytics company focused on providing technology reconnaissance, horizon scanning, and wargaming capabilities to the U.S. Department of Defense Science and Technology Enterprise. And prior to that, Dr. Augustin served as senior researcher at the U.S. Army Natick Soldier Research Development and Engineering Center. While there, he built a multi-million-dollar research and development program focused on enhancing soldier and squad effectiveness through real-time psychological and physiological status monitoring, training, and performance modeling. Dr. Augustin holds a PhD in cognitive science from Penn State University, where he developed novel techniques for modeling human decision-making and perceptual motor planning. And with that, I will turn it over to you, Jason.
All right, Ted, thank you for the rousing introduction. Your check is in the mail. Welcome, everyone. I was thinking before this talk began that I'm used to giving talks in person, and of course, in this semi-post-COVID era, it's always interesting to try to deliver a talk when staring at a screen. But I appreciate that all of you are here, and thank you for joining us. So the talk today will be on emerging trends in artificial intelligence and machine learning. And let me just start by caveating the fact that AI ML is a massive, massive field, as I'm sure many of you know, and so it's not going to be possible for us to do a deep dive, unfortunately, in any particular area. But as you know, as my friends and coworkers will tell you, I'm always happy to talk about this stuff. So if you do have questions, or if you do want to engage, I would love for you to reach out after the talk. My contact information is here, and I'm sure it will be available through DSIAC as well. So with that, let's dive in. So I thought it would be helpful just to start by level setting a bit on some definitions. You know, what is AIML? It's a hot topic. You know, we have centers of excellence being stood up across DoD related to AIML. We have obviously tremendous amounts of work going on in the private sector and academia. So there's a lot of flurry of activity and a lot of innovation in this area. So it's helpful, I think, you know, especially when you have an area that's been growing so rapidly and is so hot, it can be really helpful to be clear on what we mean when we use these terms. So I will, you know, full disclosure, I borrowed these from Microsoft. I think they're good definitions of the two topics we'll be talking about today. And if you look at other definitions of AIML, you'll see similar types of themes. So AI you can think of as really kind of the umbrella term. It's really the ability of a computer system to mimic human cognitive functions. So it's building a thinking machine. Typically, that's done by using some manipulation of mathematical symbols, logic, etc. But the goal really is to simulate the kind of thinking that people do, and certainly to build systems that can learn and respond to new information. That's a broad umbrella. It covers a lot of different sorts of activities. Machine learning you can think of as kind of an application of AI principles. It's about building models of data to help computers learn without direct instruction. So the idea is to build a system that can learn from data and can make useful predictions in some area of application. And then again, that itself, of course, is obviously a large and diverse area with lots of specifics around it. But it's important, and I'll touch on this a bit towards the end of my talk as well. Given the level of enthusiasm, which is wonderful to see around AIML, it's really important to kind of separate mentally machine learning from what I might term. I'm sorry, I'm just looking at a pop-up that just came up here. Might be termed as something like artificial general intelligence, or AGI. And AGI is kind of when a lot of lay people think about artificial intelligence, they're kind of thinking about AGI. They're thinking about, you know, they're thinking about HAL. They're thinking about Skynet. I tried to come up with good examples that were not, you know, did not lead to inevitable dystopias, but I kind of ran dry. But they're thinking about systems that truly are mirrors or mimics of the human mind, and that can solve the full breadth and scope and richness of tasks that people can solve. We have made tremendous strides in machine learning, in building specific models for specific use cases with specific data, as we'll see in this talk. Our progress in AGI, I think, is a lot more limited, and that's a lot more ambitious goal. So oftentimes when you're hearing people throwing around, "Hey, we just built a new AI solution," that's great. Typically what they mean is they've built a new machine learning solution, and that's just as good. But it is important to keep in mind that distinction. Okay, so again, I thought it might be helpful just to start with kind of just a brief history of the field. Again, it's a really interesting and rich history, so I'm not going to hit all the deep bits of this, but just to hit kind of the high points. Broadly speaking, research on AIML and applications of AIML date back to about the mid 50s. So the post-war era, the emergence of the first general purpose computers, which really powered both the practical implementation of AI models, but also really powered the thinking about what it would mean for a computer to think. So this is some of the early work of Alan Turing and other folks who were really thinking about what are essentially cognitive processes in terms of computation, something that a computer might be able to ultimately perform. So the first boom time for AI was really from about the mid 50s to around 1974. And this is sort of the era that's broadly considered the era of symbolic AI. And this is the era of luminaries like Herb Simon, Marvin Minsky, others. And the idea here was that we're building systems that mimic human thought processes using the tools and the techniques of computer science, which means essentially rule and symbol manipulation. So the idea was if we can encode data and then we can train, we can have a system that has rules for how to manipulate that data. At the back end, we'll get out some kind of a behavioral output that resembles something that a human might do. So this was really the sort of first pass at this. And a lot of innovation was done during this time. A lot of money flowed into this area from DoD, for example, and there was a lot of success. There was a lot of ground laid. So much so that it led to what I would say our first brush with irrational exuberance in the field of AIML. So you have Herb Simon and Alan Newell saying in 1958 that from their perspective, it would be 10 years before we had a computer that was the world chess champion. So that would have been 1968. Now, the fact of the matter is, we did get there, but it wasn't until 1997. So a bit off there. Marvin Minsky, again, an absolute luminary, and if you don't know much about Marvin Minsky, you should look into him. An absolute titan in the science. He was even more optimistic. He said, within a generation, so by the mid '80s, by the time we're all doing, everyone's at Studio 54, within a generation, the problem of creating artificial intelligence will be substantially solved. So you can see these are people who deeply knew what they were talking about. These weren't dilettantes. They were very optimistic. Well, unfortunately, the boom times of this first period of symbolic AI were followed by what's termed in the field as the first AI winter. And I of course had the obligatory Game of Thrones joke on this slide that ended up getting stripped. But the field has gone through two of these winters now, where we've had bouts of tremendous enthusiasm, a lot of innovation, but a failure to translate that into enduring sort of real world business cases, right, that can justify the investments. And that's really what happened in this first AI winter, which lasted about 6 years. The field ran into a few barriers: limited computing power of the day. Many of the frameworks and techniques that people were approaching during the symbolic AI era, while interesting, were kind of fundamentally unscalable. They required combinatorics that just did not work out at scale. They required data processing that just was not possible at scale at this time. And then in general, there was just a lack of data available to build these systems. So the boom times quickly led to the first bust. Funding dried up. DARPA basically dropped all of its funding in the area, and the field entered the first AI winter, which lasted until the '80s, when we had the rise of expert systems, which took a lot of the insights from the symbolic AI era and tried to be a bit more practical with the engineering aspects. Try to build systems that were a bit more modest in their aims and could answer actual business problems and business cases by incorporating knowledge dictionaries and things of that nature. This was also a period where we had a revival towards the end of the expert system era of connectionism, which was really the forerunner of everything that we're doing today with neural networks, deep neural nets, deep learning, et cetera. These were folks like Hopfield, Rumelhart, and McClelland. The idea was, can we get away from thinking about kind of sort of linear programming sorts of frameworks and start to try to model the way the brain works in silicon? And that was really the rise of kind of the early era, again, of neural networks through the concepts of connectionism. So that worked great for a while. We had a good run, about 7 years. And then we entered the second AI winter. And again, here, part of the problem, again, was lack of computer power. So the initial expert systems were successful. They had value, and then people wanted to scale them. They wanted larger, more complex systems to answer more complicated business problems. Well, we were still dealing with computers that were quite rudimentary by today's standards. And again, we just lacked the computing power. We lacked a lot of the ability to label and store and manipulate data. So the promise of expert systems kind of petered out, and we entered the second AI winter, which again lasted 6 years. And that brings us to kind of what is the modern AI ML era, which started in around the mid '90s and is still going strong today. I've hit on it a few times here, but really the distinguishing factor that's driven the relatively long success we've had in this most recent era of AI ML is explosions in computer power, certainly, the rise of things like cloud computing, um, the increasing availability of data, both as a driver, right? So the need for these models is largely driven by wanting to extract insights from large complex data sets, but also the fact that we need that data to build the models. So the proliferation of data has actually been really a blessing, both from a practical perspective and a technical perspective in the area of AI. It's also interesting that I think a lot of the insight from earlier eras of AI is that we did a lot of interesting theoretical work, but not a lot of attention was paid to engineering. And I think you could argue that a lot of the success, the recent success in the area of ML in particular, comes down to just rolling your sleeves up types of good computer engineering, good systems engineering. There's been a lot of work on optimizing algorithms. There's been a lot of work on optimizing data pipelines, and so on. And that kind of, while less, maybe perhaps less, glorious than some of the earlier work that Simon and Newell were working on, it's led to a lot of the practical successes. So what I'll be talking about the rest of the day today here is kind of a look that BluePath has done at the AI/ML research landscape. And what we're trying to understand here is kind of the major research topics driving the field, who are the national institutional leaders, I'm sorry, that should say international leaders, and then what trends are likely to shape the field over the next 3 to 5 years. And I'll beg your forgiveness up front for a few shameless plugs during this talk. One of them is coming right now. BluePath is putting together a report on the AI/ML research landscape. This will be broadly available. So if you're interested in receiving a copy of this report once it's released, please let me know and we will make sure to get it to you. So let me talk briefly about our methodology here. So this landscape analysis employed a variety of tools that BluePath has partnered with DSIAC on to develop for the Air Force Research Laboratory. The banner for that project is Project Horizon. So we've been building for AFRL a platform to do scientific portfolio management and portfolio analysis. So it's a web-based tool that can ingest large amounts of scientific and technical data and can identify leadership. It can analyze partnerships and collaborations. It can identify trends. It can do a variety of different analysis outputs. And a lot of that was the foundation for the work that I'm going to share with you today. So what we did is we conducted a broad search for academic journal articles and conference papers on AI and ML published in the past 5 years. So this is a look over the fairly recent history of what is a rapidly growing and developing field. We then filtered the initial document set to identify high quality relevant research. And I'm going to talk a bit about quality because when you're thinking about doing landscape analyses, understanding and appreciating quality of the data is absolutely vital. So I'll talk a bit about that. Then we applied a variety of applied natural language processing techniques that we've developed to cluster that data and identify emerging technical trends. And from there, we can think about leadership and so on. So that's a high level. And again, I'm happy to provide more detail on any of this methodology if folks are interested. Let me talk a bit about the data. Always an important topic. So again, this was an analysis focused on understanding the research landscape. So this wasn't so much an analysis of the applied or commercial landscape. So our data source here was really focused on academic peer-reviewed technical journal articles and conference papers. Our data source for that that we used was Microsoft Academic Graph. It's an open bibliographic database. It currently has about 246 million documents in it that covers journal articles, conference papers, covers some patent data, books, graduate theses, data repositories, a variety of different data. It's openly available from Microsoft, and it's really been a boon to kind of the open science analytics community. There have been a variety of, if you're curious about how MAG might compare in terms of data quality to something like Scopus or Web of Science or another similar type of database, there have been a variety of independent analyses that have been done by folks outside of our organization, certainly, that have found that the coverage compares quite well, the data quality compares quite well to what are often considered the gold standard databases. So we have confidence that the data coming out of MAG are both robust and comprehensive. And I'll just note that the MAG currently powers a variety of open source research tools, including Semantic Scholar, which if you're familiar with this area, or if you do any kind of literature searching, you're probably familiar with the quality of Semantic Scholar. That's a bit about our data. Now, again, you have to start, of course, obviously with a quality data source. That's a requirement. But even then, we've done a lot of these sorts of landscape analyses on a variety of topics. Material science. We've done previous work with AI. We've done work on hypersonic weapons. We've done a lot of these over the years. And one insight that has really, been kind of drilled into us as we've done this is the importance of filtering out low quality research. Especially in an area like AIML that's growing so rapidly, there is a lot of work out there that gets published in lower tier journals, lower tier conferences that frankly is not very good. It's highly derivative, it's low quality. It's the kind of work that if you include it in your landscape analysis, you could very easily get a skewed picture of what's actually going on in the field, what's really interesting in the field. So our goal was to start by filtering out any of this low quality work so we can get a purer understanding of what the really exciting stuff is that's happening in AIML. There's a long history and many approaches out there and many metrics out there for looking at publication quality, and really almost all of them use citation based measures. So the number of times an article was cited by other papers, for example, or the number of times articles in a particular journal were cited in other journals or conferences. So citation-based analysis is really kind of the bread and butter of a lot of impact analysis. And that sort of makes sense. I mean, being cited is a good indicator that you've done something that other people find interesting and useful. The problem is, and again, there's a lot of literature on this. It's really fascinating literature, but citations are a problematic metric on their own. They're easily gamed. Journals actually game citations. So some journals will essentially pressure you to cite other papers appearing in that same journal because that drives up the journal's impact factor. So journals game citations, individual researchers clearly gain citations. There's a lot of self-citing that goes on. There's a lot of sort of, you scratch my back, I'll scratch yours with citations. So citations, really are valuable, of course, but you have to appreciate that they're very easy to manipulate. There are, of course, other metrics out there. Alt metrics is one that many people may be familiar with. There are approaches to using social media mentions and social media discussion to find interesting research, and those are all also quite interesting and have their place, but also have their own unique problems. So this is by no means a solved area, but it's certainly an area that's important to be cognizant of. So let me tell you a bit about our approach here to how we did this. So in this particular analysis, we started with an initial data set from our initial search of around 363,000 documents on AI and ML. Again, this is journal articles and conference papers. Those came from around 10,500 journals and 2,200 conferences. So that was our initial data set. We then looked at measuring the quality of the venues that those documents appeared in. So the quality of the journals, the quality of the conferences. The idea being, can we identify venues that publish high quality research reliably? And the way we did that is we looked at the prestige of the organizations that publish in those journals and conferences. And then we did, of course, incorporate normalized citation rates. So just to give you an example, what we would do is we would take a journal like Science, and I would look at all of the articles, not just on AIML, but all of the research that's been published in Science over the past 5 years in this case. And we looked at who's publishing in those journals. And we've developed a consensus list from several different sources of the top research organizations in the world. And we looked for the presence of those entities in the publication history of these venues. And we used a high appearance of your MITs, your Oxfords, your sort of preeminent research institutions. We use that as a marker that the venue is publishing work from really the leading the leading sources in the field. We used that measure to filter on quality, and we got ourselves down to about 99,000 documents from 1,000 journals and about 856 conferences. So you can see we really cut we've left a lot on the cutting room floor. And you could certainly argue that is there value in being more or less conservative with this? We took a fairly conservative approach here. But again, I think the point is it's really important to think about quality and think about filtering on quality when you're doing this kind of landscape analysis. Just briefly to show you, this is kind of the distribution on the left here of our kind of the two components of our quality score, which were this prestige of the publishing organizations and the citation rates. You can see there's the distribution. Interestingly, and this makes sense for AIML, you'll see a lot of the higher prestige venues were journals, and a lot of the higher cited venues were conferences. This is an interesting field in that a lot of work that gets highly cited tends to come out in conferences first. And there's a list here on the right of the top 10 venues based on our metric, just so you can get a sense of what's here. And if you know the field, you should probably look at this list and you should recognize certainly a lot of these venues. Okay, so with that all as preamble, let me get into the actual landscape analysis. So first of all, again, this is not going to be a surprise to anybody here on the call. I do see some questions popping up. I'm going to leave time at the end, and we'll hit those at the end. So thank you for those. We do see that AIML is obviously growing. There was a tremendous acceleration starting in about 2002 up to around 2010. I will note that the publication output, as a proxy for research output, has kind of leveled off over the last several years, and you can ask. There's a variety of reasons why that might be, but that is a pattern that we're seeing. In terms of who leads overall, again, this may not be a surprise to a lot of people, but really the global AI landscape is really being led at this point by the United States and China. You can see this is a choropleth showing output by country over the past 5 years. And again, this is data that's been filtered for quality now. So this is quality AIML research. And again, it's the pattern's quite obvious, right? It's the US and China, and then there's a bunch of sort of second tier players in the field. In terms of the United States, we can ask, who are the leading research institutions in the US? So from the United States perspective, who's really driving the train? And again, if you look at the list, it's a lot of organizations that probably are not surprising. So we see Stanford, we see Microsoft, MIT, Google, Harvard, UC Berkeley, Johns Hopkins, IBM, Georgia Tech, and USC. These are the top 10 US institutions putting out AIML work over the past 5 years. And you can see there, it's an interesting mix of academic institutions and industry players. I've highlighted those there on the right of the graph, and I also pulled. I thought it would be interesting to look at R&D investments by the industry players. So I went and I pulled from their financial filings with the SEC. I pulled the total R&D budgets for the industry players last year. And again, this is not just investment in AIML, certainly. This is investment in a lot of areas. But just to give you a sense of the scale, you can see, Microsoft pumps, around $21 billion into R&D every year, which is a massive amount. Google puts about 28 billion in. IBM about 6 billion. So these are companies that are making huge investments in R&D. And again, not all certainly in AIML, but I would argue certainly in the case of Google, if you look at what they're doing, an awful lot of it is AIML focused. And what's interesting is that these companies are also contributing to the basic technical literature. So a lot of the my special area of interest is natural language processing. And a lot of the really interesting work in NLP, some of the most seminal papers in NLP over the past few years have come out of Google, Facebook as well, but certainly Google. So this is an area where it's not just being led by academic institutions. If we shift our view to the international scene, so we look outside the US, who's leading globally? Well, guess what? It's all China. And again, I think it's important to note that we have filtered out low quality research. So there's often, I often run into a perception that China, they're investing a lot, they're publishing a lot of papers, but it tends to be, garbage research, it tends to be low quality. Again, we have filtered that low quality work out, and China is still very much in the driver's seat in the international picture. So I think it'd be very difficult to argue at this point in late 2021 that China is not a serious player doing high quality work in AIML. you can see the Chinese Academy of Sciences is the leader here. I have another slide on CAS in a moment because you can kind of think of CAS if you're not familiar with them. And I'll apologize up front to any of my China colleagues who are on the phone if I misconstrue this. But you can think of CAS as really kind of an umbrella organization in China. They're a little bit like kind of our NSF NIH if our NSF NIH also ran a bunch of specific research institutions. They're kind of an umbrella organization. Tsinghua, Peking, Shenzhou, Tong. Again, I apologize for the pronunciations and so on. The only two centers outside of China that we're seeing in the top 10 are the National University of Singapore and Imperial College London. We're doing relatively small amounts of work in the grand scheme of things. I mentioned that CAS is kind of an umbrella organization. They have a variety of institutes and centers, and one of the sort of key focus areas inside CAS is the system of state key laboratories. So in China, there are a system of these state-run these state laboratories that can be a mix of private work, but also public work that are all funded by the Chinese government. So it's interesting when you're looking at leadership at CAS, it can be very interesting to look at, okay, what specific laboratories within CAS are doing AI/ML work, and this is a list of the top 10 based on our analysis, and you can see we have at the top we have the Laboratory for Management and Control of Complex Systems. We have obviously robotics, optics, computer architecture, information security, micro nano energy and sensors, molecular imaging, human machine intelligence synergy systems, information security, remote sensing, and then coming in at the bottom here, we have vegetation and environmental change. So I think what's interesting about this is two things. First of all, broad investment, broad production of AI/ML work across a variety of different centers inside CAS. So there are a lot of pockets of this work happening inside China. I think the other interesting takeaway from this slide is the diversity of subject areas. So China is investing in AI/ML work across a variety of sectors, ranging from control of complex systems to robotics, which is an obvious application, but even things like optics and energy systems and even environmental systems. So they are really pursuing a broad-based strategy founded on AI/ML research. Okay. Given the dominance of the U.S. and China in AI/ML, it's natural to ask, well, what are we doing? How are we partnering with them? So what I'm showing here are the most active U.S.-China collaborations over the past 5 years. There are other collaborations certainly in this data set. These are the most active ones, and I'm showing this as a heat map. And the takeaway here is that in terms of active collaborations, you can see Microsoft has a tremendous amount of collaboration with various Chinese research institutions. You can see they are really the dominant, from the US perspective, the most collaborative organization with the Chinese. From the Chinese perspective, you can see Tsinghua University has fairly broad collaboration across the board. It's interesting though, in a lot of areas you see huge amounts of collaboration between China and the US. In the area of AI/ML, we looked at what is the overall collaboration rate. So if I look at all of the research that's been produced over the past 5 years, how often do we see Chinese and American authors together on the same paper? And as it turns out, that was about 6% of the data set. So the overall collaboration rate between the US and China in the past 5 years was around 6%. So I'll leave it to you to wonder whether that's high or low. I think we were somewhat surprised by how low that was. We would have actually thought it was higher. And there are potentially some reasons for that. In some cases, I will say that one thing about this analysis is, if we're looking at the industry players, if they have multiple centers, Google will have like a China research center. Our data codes that all as Google. So there may be some collaborations that we're missing here that are international, but for the most part, it is interesting that this is kind of the rate of collaboration that we're seeing. If we look at the institutions with the most U.S.-China collaboration, so if we look on the U.S. side and the China side, who's doing the collaborating? This is simply that list. You can see on the left, these are the Chinese entities. You see towards the bottom, you see Tencent is doing a fair amount of collaboration, which is a Chinese company. On the right, again, Microsoft. and you can see a variety of universities that are doing a fair amount of collaboration with Chinese entities. I think another interesting question that we're digging into is a power imbalance in U.S.-China collaborations. So there's often a perception that the way China works is that they come in and they steal our IP. So they come in and they partner with a university. The university researcher just wants to advance knowledge. They have a colleague in China. They do work together. But the question is, are our best people partnering with sort of lower tier researchers in China, and are we experiencing kind of an IP or intellectual drain effectively to China? I think it's a really interesting question, and it's one that we're looking at addressing with this data. So let's talk a bit about the research landscape methodology. Make sure this slide, great. Okay, so having talked a bit about global leadership, having talked a bit about U.S. and China partnerships, let's talk a bit about the actual landscape analysis now. So again, what we've done here is we've taken the document set that I discussed earlier, and we have clustered those documents to identify rapidly growing areas of technical research. Just a bit of a high-level background on how we do that, and again, I'm happy to provide more detail if people are interested in this. We use a text embedding model to convert titles and abstracts into feature vectors. So basically, we take the unstructured open text and we convert it into sort of a numerical feature vector that we can train a model on. We then reduce those vectors to a lower dimensional space. And again, I'm happy to go into the math behind that. And then we cluster those vectors in this case, using a density-based clustering technique. This would be the point in the talk where I'd be looking at all of you, and I'd be like trying to gauge body language to see if this is all registering. So hopefully this is making sense to at least most of you. And when we did that, we ended up with around 108 specific AIML research clusters. So clusters of concrete work. Oh, thanks, Gretchen. We then grouped those. So we sort of did a low-level clustering, and then we kind of did what I refer to as mega clusters, so higher-level clusters. And from there, we identified kind of the fastest-growing trends. What I'm showing you on the right, incidentally, is just a two-dimensional projection of our feature vectors. It's admittedly kind of an eye chart. It's just there to sort of show you kind of what the sort of clustering solution ends up looking like. And you can see we do get defined clusters of research. Okay, so as I said, we took the 108 initial clusters that we got out of the analysis, and we boiled those down to 10, what we're referring to as mega clusters. And I have those listed here on the right. And again, if you're someone who's in this field or has some familiarity with the field, you'll recognize a lot of these. It's not surprising, for example, that there's an awful lot of work happening in computer vision, right? That was sort of the most dominant area of technical innovation. Health applications is a huge area of work. And I'm going to go into each one of these in more detail, but just to sort of frame at a top level. NLP, learning algorithms, commercial applications, HCI, consumer applications, multimodal computer perception, which I'll explain in a bit, cybersecurity, which is an interesting one, and information retrieval. So if we try to carve the landscape of AI/ML at its joints, these are kind of the 10 fastest growing, kind of hottest, most dominant areas. And again, certainly one thing, if you've done landscape analysis, you would know, you know, of course, that, you can always debate different ways to do clustering, of course. And so you may look at this and think, maybe your distribution of subclusters might be different than mine. Maybe you'd quibble with wording a bit. And that's all fair. But I think again, if you look at this list and you compare it to broader discussions in the field, it's clear that these really are the dominant topics in AIML today. So what I'm going to do now is I'm actually going to tick through each one of these topics, and I'm going to try to provide you a little bit of insight into what's going on in each one. Again, this is a lot of work, so it's not going to be possible for us to do a deep dive in any one of these. Each of them is fascinating in its own way. So I'm just trying to sort of hit the wave tops for you and give you a sense of kind of what's going on and kind of who's leading and so on and so forth. So computer vision. And on the left of all these slides will be formatted the same. You'll see on the left, I give you counts of the publications from our data set, the percentage of that publication count, and then a growth rate. This is a year over year, an average year over year growth rate over the past 5 years. So we can see computer vision work is growing at a rate of about 3.7% per year over the past 5 years. Key subtrends. So I mentioned with those 108 clusters, when we look at kind of what's in there, we look at the ones that are associated with computer vision. This is a flavor for some of those clusters. We see a lot of work on person re-identification, which is the ability to basically recognize the same person from different still or video images. So you can imagine if I have a CCTV network set up and I have a person walking through the area being captured by various cameras, I'd like to be able to recognize the same person in each of those images. And that's the problem of person re-identification. Semantic segmentation of scenes. This is the ability to take a picture, again, it could be a still or a video image, and really pull out kind of meaningful objects and meaningful information of it from that image. So pulling out that sort of lumpy object over there is a car, and pulling out that this even lumpier shape over here is Elon Musk getting out of that car. Apologies if you're an Elon Musk fan. My son is a huge Elon Musk fan, so all said with love. Thermal and infrared imaging, which again, trying to apply CV techniques to those types of hyperspectral image sets. There's a lot of work, again, this is probably not surprising to most of us, there's a lot of work in CV going on around getting computers to recognize human behavior and human identity. So there's a lot of work around human action recognition, which you can imagine is important for things like self-driving cars, right? So I need to detect pedestrians, I need to detect behavior in the street. Face recognition, and also the flip side of that is synthesis. So many of us might be familiar with deepfakes and concerns over artificial imagery that can really compellingly impersonate even celebrities. So there's some tremendously frightening / interesting videos out there of completely synthesized video and still images and even audio, perfectly mimicking presidents, celebrities, and so on. So that's what this area is about. There's a lot of work on image quality enhancement. There's a lot of work on depth estimation, change and anomaly detection. So that's kind of a flavor for the subfields in computer vision that are hot. In terms of leadership, again, this will be a consistent theme. You're going to see a lot of Chinese flags, and you're going to see a lot of American flags. So these are kind of the leaders in CV. And again, if you look at who's playing in this area, it makes a lot of sense. Carnegie Mellon, one of the leading computer vision programs in the world. Google, obviously, with autonomous vehicles and so on and so forth. I'm also providing on each one of these slides on the bottom right a sense of kind of what is the US versus China balance. So if I look at research where there's an American author and I look at research where there's a Chinese author, am I seeing more of one country represented than the other? And in this case, we see computer vision. So this is an index this is an index of relative focus. You can think about it. So are there areas where the US tends to be more heavily playing and areas where China tends to be more heavily playing? Computer vision is one where we see more work coming from Chinese researchers overall. Interestingly, the collaboration rate, again, if we look at that metric of how often do I see Chinese and American researchers on the same paper, the collaboration rate in CV is actually higher than the overall rate. It's around 11%. So there's a good amount of collaboration going on between the US and China, specifically in the area of computer vision. Switching to health, huge area. And this is an area where really the US is really leading the way. We have a lot of US work going on health applications of AI and ML. And when you look at what's being done, it's really ticking all of your leading causes of death and disability. So there's a lot of work on AI ML techniques for diagnosing and managing diabetes, heart disease, cancer, various mental health disorders, seizures. There's a lot of work on segmenting medical images from both X-ray to PET to MRI. Not surprisingly, the past at least couple of years, there's been a real surge in work in the epidemiology of infectious disease. There's a lot of COVID-19 work, not surprisingly, going on in AI/ML. There's a lot of work on using AI/ML techniques to drive pharmaceutical research, to drive drug discovery and drug testing. And then surgical robots would fall into this category as well. Natural language processing, again, near and dear to my heart. This is the act of getting computers to understand and produce and analyze human language. We see text classification, text embedding. So again, this is converting text into feature vectors that computers can work with. Text summarization is really interesting. So this is the ability to train a model to summarize long texts. So I could provide a full technical report and have an ML system write me the blurb that summarizes it. Neural machine translation, obviously a huge area. There's a lot of really interesting work that's growing in the area of multilingual NLP. So how do we get systems that are bi and multilingual and can recognize and work with multiple languages, even when those languages are mixed in the same text, which is a challenging problem. And things like named entity extraction, also quite important. And you can see the leaders here. And again, this is an area where we see an awful lot of work from the US, but also a good amount of collaboration between US and Chinese researchers. Learning algorithms. This is kind of a catch-all for fundamental work on learning techniques. So when you think about deep learning and you think about things of that nature, this is a lot of the fundamental work on those algorithms. Things like domain adaptation. So if I train a model on one domain, how do I get it to work with another domain? Neural architecture search, which again, if you're afraid of Skynet, this is not going to give you the warm and fuzzies. This is basically teaching neural networks to architect themselves and find more optimal architectures on their own independently. Metric learning, graph neural networks, which are neural networks that are built to function on graph data as opposed to something like a tabular data form. There's a lot of work going on in AIML right now on trying to learn from sparse data and limited data sets. So this is learning on sparse data. This is zero-shot and few-shot learning. The biggest bottleneck, honestly, in a lot of cases these days is having enough data, having enough labeled data to train a model on. And so there's a lot of work trying to look into, can we build good models with less data? How do we use less data? How do we use, can we generate new data? Can we remix data? So there's a lot of work on trying to do more with less data. This is also an area where you see a lot of discussion around fairness and bias in AIML, which is not maybe a technical research topic, but there's been growing recognition that a lot of our models are, if there's bias in the data, there will be bias in the model. And there have been some very high profile cases of this. Microsoft had a stumble with this a while back. There have been a lot of cases where it's been shown that models that are trained to recognize images and label images tend to have a lot of racial stereotypes built into them. There's obviously growing awareness of issues around bias in social media and the kinds of content that gets promoted by algorithms on social media. So this is a growing area of concern and interest that would fall under this general idea of how do we build learning systems. You can see the leadership here. Again, a lot of American work. Not surprisingly, Google's doing a lot of work in this area. And again, a good amount of collaboration. Commercial applications. This is a kind of a grab bag for just sort of industry types of applications. You can see everything here from photovoltaics to construction site safety modeling to manufacturing control to stock market prediction, a variety of different areas. China's doing a lot of work in here. The balance is fairly even between the two countries, and the collaboration rate is actually fairly high. So you can see this is an area where, again, China is heavily invested in trying to apply AIML to optimizing commercial activities, industrial activities. HCI and robotics. So this is human-computer interaction and robotics. This is self-driving cars. This is traffic flow prediction. This is UAV work. This is human-robot and robot-robot interaction and things of that nature. This one, interestingly enough, if you look, the growth rate is actually negative. It's essentially flat, but you can see we've actually dipped into the negative here. So you might wonder, there's all this work on robotics. Why is the research output declining? And I think there are a few different reasons for that. One might be a shift from, again, research, which is being published in the open literature, to patenting potentially, and moving research inward to proprietary work that is not published. So when you look at that growth rate, just keep in mind, this again was an analysis based on the open research literature. So we would love to follow up this work with a patent-focused landscape analysis, for example, which might show which actually might show positive growth in this case. Consumer applications, kind of a fun category. There are actually a surprisingly large number of AIML applications in food, menu recommendation systems, and things of that nature. So it's sort of interesting. And you can see there's a lot of sports applications and analytics, as you might imagine, music recommendation systems, VR, etc. Not a large area, an area that's not growing tremendously. But again, this is a research analysis. A lot of this is really stuff that's happening kind of in the applied and commercial sector. Multimodal computer perception is sort of the parallel track to computer vision. This is getting computers to perceive and work with other sorts of signals. There's a lot of work going on in audio perception, so acoustic scene classification, separating audio sources that are mixed in an incoming signal. So that might be something like separating out individual voices or separating a voice from a noisy background. There's a lot of work going on in underwater imaging. Texture classification, which again, if you're building a robot, you'd like to give that robot haptic perception, right? You'd like to have that robot be able to sense the environment tactily, and there's a lot of work there. And again, a fairly mixed bag. There's actually quite a lot of UK researchers interested in this particular area. Relatively low collaboration, though, between the US and China. Cyber is a huge one. Not a lot of work recently, but you can see it's growing. Is the fastest growing area in AIML is applications in cybersecurity. This is biometrics. This is automated malware detection. This is software defect prediction. This is forgery detection. There's a lot of work and a growing amount of work here in applying AIML to get ahead of cybersecurity threats. And this, I think, you could focus an entire talk just on this area. It's very interesting. A lot of US and China work. Moderate collaboration, and you can see this is an area where we are largely leading. Information retrieval. This is pulling information out of databases and putting relevant information in front of people. This is things like recommendation systems, knowledge graphs, which are a really interesting development in how to think about linking data and different types of data in ways that go beyond what's possible with traditional relational databases. So interestingly, most Google searches these days are served by a massive knowledge graph that Google has built, linking at the phrase level, linking concepts and intentions from individual phrases on individual websites in a way that they can find very focused, very relevant work for people. And again, that's based largely on this knowledge graph type of technology. Okay, so we're getting close on time, and I do want to leave some time for questions. So let's just talk about a few takeaways here. So obviously, dramatic progress in ML over the past 20 years. US and China are leading, but there's no doubt that we have seen we're in a definite boom time for this area of work. I'll just again reiterate: China is producing a lot of quality AIML research. So if you hear people say that it's derivative or it's second rate, it's really not. They're doing a lot of really cutting edge work. I read a lot of papers. And an awful lot of them have fully Chinese authorship that are quite good. This is an interesting research landscape in the sense that US tech companies are the prime movers in a lot of cases. Many times when you do a research landscape analysis, the leaders are research institutions, universities. But this is a case in which tech companies are putting out a lot of basic research. So they are moving the field forward fundamentally in interesting ways. As I mentioned, cybersecurity, a major growth area for AIML. So if you're watching something in AIML, I think cybersecurity applications are a very interesting one. And again, this analysis focused on basic and early applied research. So one thing we might like to do down the road is take a similar look at the patent landscape to see if we see different patterns of behavior in the more kind of commercial and tech transfer world. Last thing I want to just leave you with before we open the floor for questions is just thinking a bit about, what are the future prospects for AIML? This is a field that has gone through 2 winters. And again, you can imagine the obligatory Game of Thrones joke. Are we likely to see another one? I think on the one hand, the field has tremendous strengths behind it that it did not have in the past. So huge success in a variety of valuable commercial use cases, expanding computational power. So we've largely gotten past a lot of the computational limitations that plagued the previous eras of AIML. The rise of open source tools. So a lot of the really best AIML work ends up getting released open source. and a lot of it is done in languages like Python that are broadly accessible. It's led to a lot of open innovation in the area that's really driven a lot of interesting things forward. That's been coupled with open data sources. We used one in this analysis. MAG is an open data source, and there's a lot of open data out there that people are using to train models to do interesting things. There's also a lot of interesting benchmark data sets that we can use to gauge the performance of different models. And then cloud computing has been a huge boon for AIML. The ability to push large models to the cloud and not have to have on-prem, very expensive computer resources has been a massive gain for democratizing this work. At the same time, there are some threats I think we need to keep in mind. If you're familiar with the Gartner hype cycle, you could argue that in some cases anyway, we might be near sort of a peak of inflated expectations around AI, ML, data science, those sorts of things. There's been a lot of investment. Everyone's putting money into it. Everyone's ramping up, hiring, all of that. The question is, will we continue to see the kind of sustained innovation and gains that we've seen over the past few years, or is that going to start to plateau? And if that starts to plateau, what does that mean for interest and enthusiasm in ongoing investment? So I don't think a collapse is imminent, certainly, but it will be interesting to keep an eye on whether the performance in the area continues to keep pace with people's enthusiasm. Another trend that we're seeing a lot more of is the increasingly high cost of training large models. So a lot of the most performant models right now in NLP are models with billions, and that's billions with a B, billions of parameters. These are models that have to be trained on large clusters of GPU-based computers, very expensive, and honestly, in many cases, prohibitive for anybody outside of a Google or a Microsoft or a large company or industry group or government agency with deep pockets to realistically build. So we've benefited from a lot of open innovation, people in their garages, for lack of a better term, people at universities. And so you do wonder if cost may become a barrier at some point that throttles innovation. In some cases, we're also starting to see a diminishing return on model size. So the classic approach in neural networks is just throw another layer at it, just throw more nodes at it. And that tends to get you quite far, but we are starting to see places where just adding more to the model is starting to give us diminishing returns. Finally, I think there are some growing concerns in government and certainly in society around things like algorithmic bias. And there's a question of whether that might at some point lead to a public backlash against AIML being integrated and chewing on all of our personal data across all the platforms that we engage in. So again, I think the prospects overall for the field are quite bright. I think we're nowhere near another winter at this point anyway. But there are some markers on the horizon of things that may pull us back somewhat in the future. And again, I'll just drive home my soapbox point that people I know are tired of hearing me say. Machine learning is different than artificial general intelligence. So when you get the notification about that hot new AI company, you need to ask yourself, well, what kind of AI is it? And with that, I will stop. Thank you so much for your time. I'll just again plug our report on AIML landscape analysis. And with that, I will stop and would love to take your questions. So I'm kind of looking through the chat at this point. So Sharon and Ted, do you want me just to kind of like answer some of these as I look through them, or how do you want to handle the Q&A?
Yes, Jason, if you want to, you can just share the respective question or query that you're addressing, starting with the first, and kind of step through them and see how far we get.
So the slides have been distributed, and you're all welcome to them. And again, please feel free to follow up with me with specific questions. Alyssa asks, can you share the query you used to generate the initial data set? It was a very broad query. We looked for anything with the phrase artificial intelligence or machine learning in it. And that had to exist in the title, the abstract, or we have all of our documents assigned to different fields of study. So we also look for AIML in the fields of study. So that last one was important because that would net us things that didn't have exactly those phrases in them. The query development process is actually really interesting, and I could say more about that. We've done a lot of work on semantic search. So we've built a semantic search engine that you can feed text into. So you could feed an abstract into it, and it will return to you similar texts. So it's a different way of doing search that gets you around some of the sometimes brittleness of doing traditional Boolean search. And again, I'm happy to provide more information on that. Chris asks, how were you able to collect all those articles from various journals? So again, we used Microsoft Academic Graph, which is a database that Microsoft makes available. The beauty of MAG is that they actually make the entire database available. So we have running locally the full database of like 240 plus million documents. And we've built a data infrastructure that puts that into both the traditional relational database system, but also in Elasticsearch, which we use for a lot of our full text search. So again, beauty of MAG is that all of the data is there, as opposed to having to suck it through somebody else's API. Brian asks, why not representation of US government labs and R&D work, not in the universities? Is it because they are not doing work or not publishing? I think that's a great question. Again, what I highlighted in this talk largely from a wave top perspective is kind of the top 10 lists, so to speak. So I think if you look deeper in the list of people performing this work, you'll certainly see some of the government labs in there. But the fact of the matter is, when you look at who are really the top leaders, we don't see a lot of government organizations in that list. But I think you have to acknowledge that most of, certainly the university work, a lot of that is being funded by government agencies. And so this talk did not really scratch the surface on funding relationships. That's a whole other really interesting area of topics to get into. So while the work might not be getting done directly at a government lab, it certainly is being funded in many cases by government labs. Let's see. We talked about that. We talked about that. Craig asks, can you comment on how AIML has been implemented in products, taking it out of a research institution? More research in one country or another may not necessarily indicate that they are leading, only that they are growing. Yeah, and that's certainly a good point, right? So you have to be careful when people say to you, China is doing more work in this area, it's growing, or the US is doing more work in this area, it's growing. You do have to look at sort of the so what. Now, from our perspective, in this analysis, this again was a research-focused analysis. So our measure of impact was really impact on sort of the intellectual side of this, really more impact on the technical innovation and breakthrough side of it. I think if you wanted to think about impact in from the perspective of tech transition, which I think is a perfectly valid way to think about it, then you might want to look at some other data sets, which is something else that we are doing. So I think it's a great point, Craig, and it really speaks to the idea of how do you characterize impact. And again, in this case, it was about advancing the state of the art is really what this was about. But certainly from a tech perspective, you might see some other dynamics as well. Raghavir asks, AIML currently depends enormously on deep learning, which recent work has shown is very resource hungry. Could this pose a limit on AI growth? Yeah, potentially. So again, I referenced the size of these models and the fact that they have to be trained in many cases on computers using graphic processing units or GPUs. So you really can't train something like a GPT-3, which is a huge model, a huge NLP model, could not be trained on a laptop or could not be trained even on a robust desktop computer. It has to be trained on a computer with multiple GPUs or a cluster with multiple GPUs. And it's a little bit like mining cryptocurrency, very, very energy intensive. And so I do think that could be something that we start to see becoming a problem, and also just a limitation, again, from a financial perspective on who can really play in the AI pool. Gretchen, thanks. Happy to provide the information for you. Michael asks, from slide 25, could you describe zero-shot and few-shot learning? So the idea there is, again, typically the way you would train a machine learning model is you would expose it to a lot of samples, a lot of labeled data. So if I'm trying to train a classifier model, for example, to recognize a particular vehicle in a scene, I'm going to need to give it a lot of images where that vehicle is present, and I've labeled it as present, and then a lot of images where the vehicle is not present, and I have to label those as not present. So and I have to do a lot of that for traditional machine learning models, like thousands or sometimes even hundreds of thousands or millions of examples to train a good model, depending on what it's trying to do. Getting that level of data is often very, very challenging. Labeling data is super expensive, very hard to do. And so the idea behind zero-shot and few-shot learning is, can we train models that can perform on very few data samples? And in the case of zero-shot learning, can we train models that transfer learning to other tasks? So if I train a visual classifier, for example, on recognizing one car, can I then apply it to recognizing other types of cars? That would be zero-shot learning. It's effectively the model was able to do its job immediately without additional training. So that's the idea here is how do we train our models with less data? It is 5 after, so I want to be a little bit cognizant of everyone's time here. Again, I would love folks should really please feel free to reach out. Lisa asked an interesting question about quantum computing. I think this is potentially a really interesting area to watch. I think over the next 3 to 5 years, and I'm always mindful of predictions based on things like what Minsky said. So I may end up sticking my foot in my mouth, but I do think within the next 3 to 5 years, it's obvious to start applying quantum computing to AIML. Right, the gains that you should see in the ability to rapidly process large amounts of data and rapidly things like neural architecture search. Imagine if I could run neural architecture search on a quantum computer, and I could, instead of having to churn sequentially through different types of modeling, different types of architectures, I could run many of them essentially simultaneously. It's an obvious partnership that I think is going to be very interesting to watch. And I think that's it. So we did pretty well on time here. So again, thank you all. I wish I could have seen all your faces here. But I thank you so much for your time. It was a real treat to talk with you, and I look forward to following up with many of you in the future. So with that, I'll hand it back over to you, Ted.
Okay, again, greatly appreciate the insights, the expertise that you bring to bear. And just one administrative note before we log off, that again, just as you went to the DSIAC website to sign up for the webinar, you will be able to go to the website and again, go into webinars, resources, past webinars, and you can find a link directly there. This will be up on YouTube and be available as recorded for you later this afternoon. So again, if you want to revisit any topics or discussion points that might not have came across clear, or again, follow up with questions, that's available to you. You can submit the questions again directly on the DSIAC website, and we'll be glad to respond. So again, appreciate everyone's involvement.
Thank you all.